Hello and welcome to another amazing production by Advanced Math Tutors. We're going to look at deriving with logarithms and exponential functions, and this is practice worksheet 1 on the website. First problem is sine of x squared times log base 3 of x cubed. And anytime you're dealing with logarithms and you've got to derive them, the very first thing you should do is look and see if you can use your log rules to make this any easier on yourself to derive. And by that I mean this. Sine of x squared you can't do anything with. There's no rule for sine that allows you to split up x squared. But there's a rule for logarithms that have an argument, what's inside the parentheses, to an exponent, which allows us to bring this 3, the x cubed, the 3, down to the front of the logarithm. So really we can rewrite it as 3 log base 3 of x. And that's just a logarithm rule. And that's going to help us derive this thing. But for right now, once you're done that, deriving it's fairly straightforward. Start with red. Sine of x squared is going to be in red. Okay, so that's right here. Deriving sine of x squared, we're going to use the product rule. Oh, the chain rule for this, but we're using the product rule in general because it's a function times another function. So deriving sine, we derive the outside first. Cosine. What's inside stays the same. Times the derivative of the inside, 2x. All that is multiplied by the second function. So we got some multiplication going on. So plus. And that's, again, this guy's in green. Okay? Now we're going to multiply by the derivative of 3 log base 3 of x. And this is where simplifying comes in handy a little bit. Now we've got 3 times the derivative of log base 3 of x. Well, all that is 1 over ln 3 times x. And I promise you, if you didn't simplify it the way I did here first, you're going to get the same answer. It's just a little bit more straightforward, a little easier if you simplify the log first and then derive. And please make sure, I see this every year, a student will rewrite the logarithm like this. They'll bring the 3 down the front, 3 log base 3 of x, and then they'll leave it like that as if they've derived it. They'll have that in their answer as dy dx. And you haven't derived it, you just rewrote it with logarithm rules. Okay, so anyway, that's the derivative of 3 log base 3 of x. And we multiply that by the first function, sine of x squared. There you are. And what we're going to get as our final answer, we'll do it in blue, he's a good color. The final answer then is 3 and 2x are going to make 6x. So 6x cos x squared log base 3 of x plus, and this is just a fraction times all this other stuff, so you put this on top over ln of 3 times x. And there you have it, folks. Your final answer. Okay, number 2. This is, so these two functions are separated by a big minus sign, so we can handle them both separately. And we're going to end up with here, we use red, dy dx is equal to, deriving an exponential function, starts with ln of whatever the base is, times the original function, because exponential functions always repeat themselves in their derivatives, times the derivative of the exponent. Well, the derivative of tangent is secant squared of x minus, now, I should have rewrote this before I started. ln of the square root of 2x plus 4 is the same thing as minus 1/2 ln of 2x plus 4, because the square root's to the 1/2 power, and it's a square root of the entire argument. It's square root of 2x plus 4. If it had just been square root of 2x, we wouldn't be allowed to do this. But since it's square root of the entire thing, we're allowed to bring the 1/2 down, and now when we derive it, we're going to get minus 1/2 times, deriving ln is just 1 over what's inside of it. So that's 2x plus 4. You don't need the ln of e there, because ln of e is 1, and then times the derivative of what's inside, and that's 2. And in this case, the 1/2 and the 2 cancel when you multiply it all together. So our final answer is the ln of 4 times 4 tangent to the x, or 4 to the tangent x, I'm sorry, times secant squared of x minus 1 over 2x plus 4. Alright. We can box them off if it makes you feel better. Might as well. There you go. Number 3. Again, these are also separated by a big minus, so we can handle them each separately. The derivative of e to any power is e to that same exact power, as long as it has a variable in it, as long as it's not a constant, I mean, times the derivative of that power. Well, the derivative of log base 10, because there's no number there, that means log base 10, of 4x is 1 over ln of 10 times 4x times the derivative of what's inside of the log, which is 4x, the derivative of that is 4, minus log base 5 of pi is a trick. That is a number. Again, pi is not a variable, it's just a Greek letter. It represents a number in particular, so this is a constant, and the derivative of a constant is 0. Our final answer, here the 4 on the bottom and the 4 on the top are going to cancel, and it is e to the log base 10 of 4x over ln of 10 times x. There you go. That's a 4 there. My handwriting's getting a little sloppy. Okay, number 4 is a turd of a problem, but we'll do them anyway. Maybe turd's not appropriate. Maybe he's just an annoying problem. Okay, and I made it up, and you're probably more annoyed than I am, but we're gonna do it anyway. So we gotta do the quotient rule, and what we're gonna do first is derive the top. Okay, so I'm gonna write the top in red, and we'll leave the bottom as the green function. All right. So first things first, derive the top. The derivative of the top, this is going to be sloppy, I'm going to try and fit it in here, is secant of e to the x tangent of e to the x times the derivative of what's inside, which is e to the x. This part right here is the derivative of secant e to the x. Minus, now we have to derive cosecant log base 5 of x cubed. And before I do that, I'm going to rewrite that as minus cosecant of 3 log base 5 of x. Okay, bring that exponent down and makes it a little bit nicer for us. So first things first, we derive the cosecant. Well, the derivative of cosecant is negative, which is going to make this negative a positive. Cosecant of what's inside, well, that's 3 log base 5 of x times cotangent of what's inside, 3 log base 5 of x times the derivative of what's inside. Well, the derivative of a logarithm, 3 log base 5 of x, is 3. He's going to end up on top, over ln of the base times what's inside, x. Now we would multiply by the derivative of what's inside of that, but that's just 1. So this is a gigantic nasty mess. This right here, this will make him a bracket, is the derivative of the top. We're going to multiply that by the bottom, ln of x. All right, now I'm going to move down here, but this is all in the same line, okay? Minus the derivative of ln of x is just 1 over x times the original top numerator, which was secant e to the x minus cosecant log base 5 of x cubed. You can rewrite this with the 3 out front, it doesn't matter. And we need one more parenthesis there, and all of that is going to be over ln of x squared. I guess I'll write you in green since that's our pattern. Okay, so the hard part here wasn't the quotient rule. That's derivative of the numerator times the bottom denominator minus derivative of the denominator times the numerator all over denominator squared. That's not hard, that's old hat for us. And it also wasn't deriving the bottom. The derivative ln of x is 1 over x. You can see how little the green takes up for this problem. The real problem was deriving the secant and the cosecant with the e to the x and the log inside. That's just a big nasty mess. But we took our time, we did it, there it is. Number 5, find the tangent line to the graph of this function when y is 0. So all tangent line problems are the same. You're looking for a point, and in this case, our point is xy, right? But y is 0. They told us when y is 0. Okay. And we need a slope. Well, the slope is going to be in the form of dy dx at this point, whatever point we're looking at. So something 0. That's what we need. We need what's his x value and what is our slope at the point. Well, let's find the x value first. We find x by plugging y equals 0 into this equation, because that's the relationship. So we're going to have e to the 0 minus x squared times 0 has to equal ln x. E to the 0 is 1, x squared times 0 is 0, so 1 equals ln of x, which means, rewrite this exponentially, e to the first power is x, which means x is e. So our point is e0. Now we need the derivative of y with respect to x at that point, e0. That's what this little bar means. This means find dy dx when we're at the point e comma 0. Well, to find that, we got to get dy dx in an equation, and we're going to derive. We'll do this in blue. The derivative of this thing is e to the y times the derivative of its exponent, which is dy dx, minus x squared y. We got to use the product rule. And anytime you do the product rule and there's a minus out front, you should put your derivative in parentheses because a minus is going to distribute. So derive the first, that's 2x times y, plus x squared times the derivative of y is x squared dy dx. There we go. And that's going to equal derivative of ln of x is 1 over x. And when we solve this for dy dx, you can do this with me here. 1 over x is going to stay on this side because it does not have a dy dx. Minus this thing, minus 2xy, I'm going to add that to both sides, so plus 2xy over here. Over, now on the left-hand side still would be e to the y times dy dx and negative x squared dy dx. Factoring out dy dx and dividing leaves us with this guy. Okay. So this is our derivative. We need this at the point e0. So at the point e0, this is going to equal 1 over e minus 0 over e to the 0 is 1 minus e squared. And since we don't want a complex fraction going on here, I'm going to multiply the numerator and denominator both by e. So e over e, and that's going to give us 1 in the numerator over e minus e cubed. There we go. So now that we have the slope and the point, the tangent line becomes y minus the y value, which is 0, is equal to the slope, which is 1 over e minus e cubed, times x minus the x value at the point we're interested in. So that's e. There you go. There's your tangent line. And technically you don't need the y minus 0 there. Let's move him over here. There we go. Okay.